Today we're going to continue our work with representing probabilities visually using what are called tree diagrams, and we'll also take a look at Bayes' theorem. The question, though, that we're attempting to answer is how do we visually organize conditional probabilities? How do we visually organize conditional probabilities? And really, the best way to organize a conditional probability is using what is called a tree diagram. And a tree diagram basically has a branch for each outcome. And then each branch produces a conditional outcome from that outcome, from that outcome. And then to find final probabilities, we can multiply down the branches for final probabilities. For example, let's say we have an urn with 5 blue and 3 green marbles. And you will draw out 2 marbles without replacement. We are being asked to make a tree diagram to model the possible outcomes and probabilities. So what we need to do is we're going to draw a branch on this tree for every decision point. So the first decision point is the very first draw. So this represents the first draw. And off that first draw, we could end up with a blue marble, or we could end up with a green marble. Now you can see there's a total of 8 marbles, 5 plus 3. So the probability of getting a blue marble on the first draw is 5 out of 8. And the probability of getting a green marble on the first draw is 3 out of 8. But we're not done there because we're still going to draw another marble. And that marble could be either blue or green. And it doesn't matter which color we got first, we're going to have the same possible outcomes. It could be either blue or green on this second draw. And so you can kind of see that if you follow a draw down, if we want a green first and a blue second, we'd go down the green line and the blue line, and that represents green first and blue second. Or if I wanted a blue then a green, we would go down the blue line first and then the green line second, and we'd end up with the blue-green combination. But first, let's fill in the individual probabilities, because on the second draw, things have changed. If we go down the left side, where the blue was drawn first, and if we want a blue on the second draw, there's no longer 5 blues left to pick from. There are only 4 blues left to pick from. And there are only 7 marbles left. So we only have a 4 in 7 chance of getting a blue marble on the second draw, given the first draw was blue. Similarly, with the green option, if we want blue then green, tracking that down, there are still 3 green marbles left. But now the total is only 7 marbles because 1 has been drawn out. A blue one has been drawn out. Similarly, on the right side of the tree diagram, if green is drawn first and then I want a blue on the next draw, there are 5 blues to pick from out of the 7 marbles that are left. But with the green, there are only 2 marbles that are green left out of the 7 marbles that are left. Now, to get my final probabilities for each of these possible outcomes, we just have to multiply down the chain. So if I want a blue-blue outcome, what I'll do is I'll multiply the 5/8 times the 4/7. And when I multiply 5/8 times 4/7, we get a probability of 0.3571. Now, if I want blue, then green, we multiply down those probabilities to get the blue-green possibility. 5/8 times 3/7 is 0.2679. Going down the next path, we go green, then blue. So if we want a green marble, then a blue marble, that probability is 3/8 times 5/7, which turns out to also be 0.2679. I think the other one was 2679 also. I wrote it down wrong. The last track is going down the green and then the green. So if we want 2 green marbles, green then green, we'll multiply the 3/8 times the 2/7 to get the 0.1071. And now we see all the different possible probabilities for drawing 2 marbles out of this urn without replacement. And we can use that table to find things like the probability that both are the same color. Well, both the same color would be a blue-blue or a green-green. And then we subtract the overlap, but there's certainly no overlap with blue-blue and green-green. So we'll just add those together. And actually I should do this in red. 0.3571 plus 0.1071 will give me the probability that I get 2 are the same color of 0.4642. One more example. What's the probability that I get at least 1 blue? Now, I could do this a couple ways. One way is I could say these first 3 options each have at least 1 blue. But that's a lot more work than saying, let's look at the complement, and let's subtract off the only one that's left from the absolute probability of 1. We know all the probabilities are 1, so we subtract out the probability that doesn't satisfy what we want. If we subtract off the 0.071, we'll end up with our probability of at least 1 blue of 0.8929. And that's how using a table can greatly facilitate our conditional probabilities and their various calculations. But one very important application of using these tables is to facilitate what is called Bayes' theorem. And Bayes' theorem is a way to find a conditional probability, like the probability of B given A, using known values of the probability of the probability of A given B. In other words, the given values are backwards from the given values that we want. Now, Bayes' theorem officially says that the probability of B given A is equal to the probability of both, the probability of A and B, divided by the probability of the given information, or the probability of A. But we might not know the exact probability of A, but we do know the probability of A given B. And we can add to that the probability of A given it's not B. In other words, we combine all the A probabilities together to build that denominator. And that last part, that not B, it may be several options. So we might need to add 3, 4, 5, 6 things that are the not B's. But we have to basically add all the combinations of the probabilities of A given the other stuff. This formula is not worth memorizing because it is always easier to do this on a tree. The tree makes this easy. And I'm going to show you what I mean with a couple examples. Let's say a marketing company predicts 90% of new products are profitable. However, the marketing firm isn't perfect. Only 70% of those products predicted to be profitable actually are. In addition, those predicted to be not profitable (20%) actually are profitable. So let's say we've got some product and it turns out that it was profitable. That's given to us. Given a product was profitable, what is the probability? It was predicted to be profitable. So it was profitable. What's the probability it actually was profitable? Let's make a tree to model this. First, the marketing firm looks at it and they say, yes, it will be profitable or not. We are told the company predicts 90% of their products will be profitable. Therefore, the complement, 10%, must not be profitable. And that's actually not just profitable, but that's a prediction of profitable and a prediction of not being profitable. Because then the next branch, we're going to look at it actually is profitable or it's not profitable. Were they right or wrong? It actually is profitable or it's not profitable. We are told 70% of those that are predicted to be profitable actually are. So if I go down that they're predicted to be profitable, they actually are. 70% are, and the rest, 30%, are not. Of those that were predicted to be not profitable, going down the not line, 20% actually are. So 20% is on the right side, and the rest, 80%, are not. Going down the lines, multiplying 0.9 times 0.7, the first branch is a 0.63% probability. 0.9 times 0.3, there's a 0.27% probability. Next branch, 0.1 times 0.2 is 0.02. And 0.1 times 0.8 is 0.08. So for my actual probability statement, it's asking, what is the probability it was predicted to be profitable? The probability that we predicted it was profitable, given it actually was profitable, given it actually is profitable. Well, we know conditional probabilities are the probability of both divided by the probability of the given information. So the probability of both, where it's predicted to be profitable and it actually is this far left branch here. That's 0.63. That is going to be our numerator, the 0.63. The denominator then is going to be the probability of the given information. The given information is that it is profitable. The is occurs in two locations. The is the left side of both branches. The is profitable. Both of those together make up my sample space. So I take the given information and I add those pieces together, 0.63 plus 0.02, and that gives me 0.63 out of 0.65, which gives me a probability that it was predicted to be profitable, given it actually was, of 0.9692. And that is how Bayes' theorem helps us reverse the given probabilities in our table. Let's do one more of these Bayes' theorems with a little bit more detail in it. Let's say Bob drives to work %40 of the time. He takes the bus 50% of the time. He walks 10% of the time. So that's 100% of the time how he gets to work. The probability he will be on time is 90% if he drives, 60% if he takes the bus, and 30% if he walks. If Bob arrives late, that's our given information. Bob has arrived late. What is the probability he took the bus? Well, let's make our tree diagram to summarize what happens. He actually has three things that can happen initially. He can drive. He can take the bus, or he can walk. In fact, we're given probabilities that he drives 40% of the time, takes the bus 50% of the time, and walks 10% of the time. Once he does that, he will be either late or on time. Doesn't matter which method he takes, he will be either late or on time. He will be either late or on time. We're told about the on-time half. If he walks, if he drives going down the drive, he will be on time 90% of the time, or 0.9, which means he's late the rest of the time, 10%. The bus, we're told, he is on time with the bus 60% of the time, which means he's late the rest of the time, 40%. But if he walks, he's on time 30% of the time, and he's late the rest, or 70% of the time. Multiplying down the chain, then, driving in late is 0.04. Driving in on time is 0.36. Busing late is 0.20. Busing on time is 0.30. Walking in late is 0.07. Walking in on time is 0.03. We are asked to find the probability that he took the bus given he arrived late. I like to start off by marking all of the given information. So given he arrived late. Late was our left branch. Late, late, late. What we're looking for is the probability that he took the bus and was late. So what we're looking for is the 0.20. Now we're ready to build our probability. The probability of both, bus and late, is that 0.20. But divided by the probability of the given information. The given information is that he was late. We marked that as a 0.04 plus a 0.20 plus a 0.07. So we have 0.20 out of 0.31, which when we divide those, you get 0.6452, almost a 65% chance that Bob took the bus, given he's arriving late. That's Bayes' theorem, and that's how we can use tree diagrams to help us with conditional probabilities. So take a look at a few of these on the homework. We will discuss these more in class, and I'll look forward to working with you then.